all these meetings, and I'll send you a link that lets you see the recording. And incidentally, that go to meeting panel, you can minimize it so that it doesn't take up so much of your screen. If you click on those two arrows that are next to one another, next to the X out, if you click on those arrows, it's like a toggle switch.
All right.
You can open it and close it. I usually keep mine minimized. That gives me the most room possible.
Yeah.
All right. What kind of stuff are you guys working on now? My guess is you're doing differentiation at this point.
So it's definitely a lot of limits, and it's a lot of delta X maneuvering and that type of stuff.
Okay.
One-sided limits and stuff like that. So yeah, I'm just gonna let me see the first problem that I probably struggle with.
I'll just go ahead and write the problem here, and then we'll take a look at solving it.
Okay. All right. Yeah. So let's see. So number 5, we got x squared y minus x squared plus 4y equals 0. And then it says test for symmetry with respect to both axes and the origin.
Okay. So it's not a limit problem.
No. This one's not. There's a lot of actually review and stuff that goes back. I don't even know if it really counts as calc, but it's in there on the review, and I'm not sure how to do it. So.
Okay. So what can I? Let's have a look at this. What should I do here? What's the best first step? That incidentally is my tutoring style, is to always ask you how to do it. If you don't know how, then I'm happy to get you started. But it's a little better if you.
Yeah, if I ask. Let's see. I know there's a. I know it has to do with like. You have to do something to get all the x's on one side or something like that, or no?
Yeah. In other words, let's take everything with an x in it and put it on the left. And let's put everything else on the right, which gives us this. X squared y. Excuse me, that's my dog howling. Let me put him on the other side of the door here. Give me a second.
Sure.
Okay. And now, what can you do on the left?
You can pull out an x squared.
Yeah, factor out the greatest common factor, leaving that. And now you can see that x squared can be solved for as a function of y. And so x is equal to what?
Is equal to square root of that you just wrote.
Plus or minus the square root of that.
Right, yeah.
In other words, every time you solve an equation by taking the square roots of both sides, always begin your answer with the words plus or minus. It's a very common mistake to make, is to leave out the plus or minus. Unfortunately, you will always lose credit if you don't put it in on a test. Okay, so that's what x is. Now, could we have solved this for y also? Yeah, we could have. Given the questions they asked you, they're asking you whether this is odd, even, and whether it has symmetry over the y-axis, correct?
No, they're asking, it says check for symmetry with respect to both axes. So the y-axis,
and
x-axis,
and the origin. Yes. If
yeah. Oh, is that what that says?
Yeah, if something has symmetry over the y-axis, it's called an even function. And if something has symmetry over the origin, it's called an odd function. And
what if it has symmetry over the x-axis?
Well, that is neither odd nor even, but you can still certainly have symmetry over the x-axis. I think in order to determine that, we might need to solve this thing for y instead of x. Let's go back and do that. Here, let me start from this step back here, and let's gather all of the y terms. You and I are probably more comfortable talking about functions where we have a y equals something rather than an x.
Yeah.
Okay, so I'm putting the y's on the left side, going to factor out a y. Should have done this in the first time, I suppose, just because it's easier to think about when we have it as a function, y as a function of x, instead of the other way around. And notice I don't have a plus or minus here. In other words, I didn't have to take the square root of both sides. Okay, now let's talk.
So did we need to?
I'm sorry, what? Kate, I lost audio for a minute. You still there?
I can't hear anything. Hold on.
Worst case scenario is if the audio, let me see what's happened here. You're still logged on.
Okay, sorry. Hey, I'm back.
Okay, and you can still hear me?
Yeah, now I can hear you. Yeah,
I could hear you the whole time. I don't know why you.
Oh, really?
Yeah, something happened, a glitch in the audio or something, but I was able to hear you the whole time. Usually, when we have audio problems like that, if they happen, they don't happen very often, but when they do, I will just call you and we can conduct the rest of the audio through phone, which works fine. It's not quite as good audio, and I'd have to run down and get my earbuds. Have to hold the phone up. What was it? What? Okay, so we've solved the thing for y.
Okay, yeah, let me write this down.
Now, let's talk about odd and even, because those are the easiest ones.
Hold on, can you go back? I'm going to copy down that.
Sure. You will get a copy of this. Everything you see, you're going to get a You're going to get a recording of it.
Okay.
And it's a YouTube file format, so you can fast forward, pause, rewind. So you do it however you want. I'm fine with you doing what you realize is the best way for you to learn by writing it down now, perhaps. But you also don't necessarily have to. In other words, you can always go back and read this. Okay?
Okay, that makes sense.
Okay.
Yeah.
So let me scroll down so I have a little writing room. Unfortunately, my eraser doesn't work on this. I'm not quite sure why. All right. So if I'm going to call this f of x instead of y, because that's what it is it is a function of x. X is the only variable that appears on the right side.
Yeah.
Okay. So for odd functions, which is symmetry about the origin, f of negative x has to equal minus f of x. For even functions, f of minus x equals f of x. A typical function would be y equal x squared. Okay? In other words, if I plug in minus x for x, well, I still get x squared. So that's an even function. And that's one way to memorize the difference between these two, is that's an even exponent. If I had y equal x cubed, now if I plug in minus x, I get minus x cubed, which is an odd function.
Okay. Yeah.
It satisfies this condition. This is what you have to have symmetry about the origin, and this gives you symmetry about the y-axis. We'll get to the x-axis in a bit. But for the moment, we'll figure out whether it has symmetry about the y and the origin. Those are the two easiest tests. So let me apply that test. Let's figure out what f of minus x is. Well, clearly it's the same thing. In other words, it's minus x squared over minus x squared plus 4. Since that is x squared over x squared plus 4, that's equal to f of x. Therefore, that is even. This function is even. It has symmetry with the y-axis. Not odd. If it would have come out to be minus f of x, then it would be odd. It would have symmetry about the origin. I don't think anything has symmetry about both. I can't think of a function that would have symmetry about the origin. And if we look at the two examples I gave, y equal x squared, it's a parabola, clearly has symmetry about the origin. If I look at y, if I look at y equal x cubed, that's symmetry about the origin. Okay?
Yeah.
Now, if I look at, if I'm trying to determine symmetry about the x-axis, something that maybe looks like this, notice one thing, that is not a function.
Right.
If you do not have a function, you do not have symmetry about the x-axis. In other words, I'm sorry, I stated that wrong. If you have symmetry about the x-axis, you do not have a function, because it's always going to fail the vertical line test.
Yeah.
Okay. Now, is this, we've got y equal x squared over x squared plus 4. That's a function. For every value of x, I have a single value of y. In other words, I never find a situation where a given value of x gives me two different answers. So, no, it doesn't have symmetry about the x-axis. And what I'm going to do now, are you familiar with Wolfram Alpha?
No.
Let me introduce you to it. It's an excellent online, it's more than just a calculator. It does calculations better than, what kind of calculator do you use? The Inspire or the TI-84?
TI-84.
Okay. Well, it's definitely superior to that, I believe. It's been a while since I've used the 84. I've been using Inspire for a couple of years. Can you give me this function again? Let's see. It was x squared y plus
minus x squared
minus x squared
plus 4y
plus 4y. Let's see what this thing looks like, and then we can verify. Are you allowed to do this? Are you allowed to put it into a calculator and And
yeah, you are actually. So I'll probably do that.
All right, well, it's got our answers. The roots are y equals that.
Yeah.
You know what? Let me put this in here differently. Y equals, and our answer was x squared divided by x squared plus 4. And I need parentheses around that. And now the beauty of Wolfram Alpha, unlike your TI, is it tells you what you put in.
Yeah.
I didn't mean for that to be a capital X. I better change it. I'm not sure what its interpretation of that would be. Okay, so it gives you two different graphs here. One is just zoomed in over the other. You can see that the bottom one is actually zoomed out. If I zoom in on it, I get the top one. This does all kinds of nice things. It tells me what my zeros are automatically, unlike your TI-84 where you have to put it on trace and figure out your zeros. This one automatically gives it to you. Gives you the range, tells you it's even, it's not odd, gives you the first derivative, gives you implicit derivative. Have you gotten to implicit differentiation yet?
Yeah.
Okay, so it gives you implicit derivatives, and it gives you limits as x goes to plus or minus infinity. So Wolfram Alpha gives you a lot of cool stuff. But the biggest thing of all is the fact that it tells you what you put in. Because sometimes when you have a really complicated function and you try to put it in on that TI-84, that's hard, getting all your parentheses straight. And then it doesn't tell you what you put in. So you don't know if you got it exactly right or not, whereas Wolfram does. I don't know if he allows you to use Wolfram. You could use them on a phone if he allows you to do it.
Yeah, I don't think so. I think it's usually strictly calculator.
Limited to that TI-84. Okay. Nonetheless, it's useful for online tutoring because it allows us to see stuff. And you can once again see that it has symmetry with the y-axis, but not the x-axis and not the origin.
Uh-huh.
All right. What else do you got?
All right. So, yeah, let me see. Let me find another problem here. All right, I'm gonna send you a picture.
Okay.
To your email.
Okay, that was. Here, let me put it back up there. Whoops. It's David Cowan 1949 at gmail.com.
All right, David Cowan.
Yeah, see, let me write it again here. David Cowan, C-O-W-A-N.
Yep.
1949 at gmail.com.
All right.
Yeah, and that shouldn't take more than, tell me when it's sent, and I should get it within like 10 seconds.
All right, I think I just sent it.
Okay. Hold on a second. There it is. Is that the email address? Is that your best email address? Okay.
Yeah.
That's where I'll send everything to.
So yeah, my question on this picture is the four graphs in the upper left. They're all part of the same problem. It's the same question. What's the minimum degree of the polynomial function for each graph? How do I do those?
Okay. Take a screenshot so I can write on it. You see these things here?
Turning points?
Well, what they are is called relative extrema.
Yeah.
In other words, there are two of them on the top left, but there's three of them on the top right. On C, there's only one. And on D, there's 1, 2, 3, 4. Well, the rule is you can only have one less than the degree of polynomial. In other words, this one's a quadratic.
Yep.
Which can have at most one relative extrema.
Okay, and the one above it would be a cubic, and then the one to the right would be a
quartic.
Up to the fourth.
Quartic, correct. And the one on the bottom right would be
to the fifth power.
Yeah. Now, that's not to say that you can't have a cubic that doesn't have any of those extrema. That is y equal x cubed.
Yeah.
But if I were to put anything else, if in other words, if I were to say y equal x cubed plus x squared minus x plus 1, it always turns this thing into where it's got some loops on it. In other words, it turns it into something like that. And now we got two relative extrema.
Yeah.
So you don't see it when it's in its parent function, just that. You don't see all those local extrema or relative extrema. But you do if it's anything, any cubic other than that, you're going to see points like that. In other words, most cubics are going to look like that. They're going to have two humps. It might go like this, the opposite way, but okay. So their question was, what is the minimum degree of polynomial? Okay. And we answered it.
Yep. And then what about the second part of that question where it says, what sign must the leading coefficient have?
Okay, let's talk about that. That has to do with end behavior.
Okay. If it's going down, it has to be negative. If it's going up, it has to be positive.
Let's take an example. Okay, something like that. End behavior is what happens to y as x goes to negative infinity. Now, when you're talking about or positive infinity, okay, that's end behavior. And when you're talking about end behavior, the only term that matters is that term there. None of the others have anything to do with end behavior. Okay? And what you're basically going to do is plug in negative infinity. I mean, they don't like to show it this way because they don't like to treat infinity as a number, but for these purposes, you can. That's equal to negative infinity. Okay? So this end behavior is clearly positive infinity when x goes to negative infinity. So the sign is not going to be what we just showed. In other words, if I had a positive coefficient in front of my x cubed term, then it's, when I substitute negative infinity, it's going to come out negative infinity. Notice if I have a negative coefficient in front of that. If I have a negative x cubed, Well, I still substitute negative infinity, but now it comes out to be positive infinity. In other words, if I put a negative sign in front of that and put negative infinity in there, cube that, that's still negative infinity. Negative negative infinity equals positive infinity. And that's what we're looking at. In other words, as x goes to negative infinity, the function goes to positive infinity.
So why are we only looking at what x goes to as it approaches negative infinity and not looking at what it goes to when it approaches infinity?
We're getting to that. I'll just do one side of it, okay?
I got you.
As it goes in this direction, positive infinity, then you're going to substitute positive infinity in there, right?
Yeah.
Notice that that's positive infinity cubed, which is positive infinity with a negative sign in front of it. That one goes to negative infinity, which is what that does. In other words, as x goes to positive infinity, y goes to negative infinity. So the only thing we have to do to figure out the coefficient, the sign of the coefficient in front of the leading term, is to figure out the end behavior. Does it come from positive infinity or negative infinity? And what you're going to find on these cubics is they're all pretty much the same. If they're like that, then the sign is positive. If they're like this, the sign is negative. When you're talking about cubics. Okay? Now, let's go to B.
Yes.
Here, we notice a quartic, so we know y equals x to the fourth plus whatever. We don't care what the whatever is. The only thing we care about is that. And what is its leading sign? Well, is that going to be positive or negative? And the way you determine it is substitute negative infinity, take it to the fourth power, you got positive infinity. Well, that's coming from positive infinity. So that works.
Yeah.
Now we'll check what happens as x goes to positive infinity. Well, you substitute positive infinity into that leading term, and you get positive infinity. So that says is that as we go, x goes to positive infinity, we also go to positive infinity. Well, that agrees with a positive coefficient in front of that x to the fourth term.
But if that x to the fourth term was a negative x to the fourth, it would still come out positive on both ends.
No, it wouldn't. Here's what it would be. In other words, negative x to the fourth, but now when I substitute either negative or positive infinity in there, that negative sign doesn't go away. That is not being taken to the fourth power.
Oh, gotcha.
I'm going to do this, and that comes out to be negative infinity. So a quartic that would have a negative coefficient would start down there and end down there. In other words, I would basically reflect over the x-axis. You're coming up from negative infinity and you're going back down to negative infinity. Whether x is going to positive or negative infinity, it's the red chart, not the other one.
Gotcha.
So, and we already know that on parabolas, you've learned a long time ago that if a parabola opens down, then the leading coefficient is what sign?
Negative.
Negative, exactly. And this one, what did we figure that was out? 5. It's got 1, 2, 3, 4. So that's a fifth, like that. What's the sign going to be in front of that?
Positive, right?
Well, let's figure it out. If it's positive, then I would have negative infinity to the 5th power, which is negative infinity, and that's exactly where it's coming from, is negative infinity. So we really only need to check one side of it. I don't actually need to do the analysis of what happens when I put in positive infinity in there, because I know that because it's an odd exponent, it's going to be positive infinity, which is what it does.
Yeah. Okay.
Okay?
Yep.
So really, the only thing you actually have to do on any of these 4 problems is determine one end behavior, either the left-handed end behavior or the right. Although I suppose in this case, you kind of need to do both, because it's a little weird that both go to infinity. But what you're going to notice is that on functions to even degrees, they both go in the same direction. On odd, like a cubic or a quintic, they are on opposite sides. One goes from negative infinity, the other goes to positive, or vice versa.
Yep.
Whereas again, with a quadratic, which is an even degree polynomial, they both go to the same side. Either they're both going to go up or they're both going to go down.
Okay, yeah. I understand that. Thank you. Now on to 41 on that same picture.
Let me scroll down here.
Yeah, right below. 41, letter C, where it says find a model for the data of the points plotted below. How do I find a model for that?
Does it look familiar?
Does what look familiar? What do you mean?
Does the graph look familiar?
It looks like a sine. It looks like a sine or cosine thing, but I don't know which one.
It's cosine. It's perfect cosine. In other words, if I were to draw a cosine curve, it would look exactly like this. Okay? This is what that looks like. That's a cosine curve with no phase shift. Now all I got to do is figure out the sinusoid function for that. Okay? Let's talk about the sinusoid function. Y equals A. You tell me which one is your standard, because not every state has the same standard. Remember this?
Yeah.
Okay. That's what we have to put this thing into, is that format. And the way we do it, a trig problem, not really a calculus problem, but that's okay. You'll find that trig is a major part of calculus. You better be up on your trig skills. You're going to need them. Okay, so just as a refresher, do you remember how to find A, B, C, and D? Once we do, we'll have the model for the data.
So A is amplitude, that's the height, right?
Yeah, there's an easy way to get A and D. A is the maximum minus the minimum divided by 2, and D is the maximum plus the minimum divided by 2. And if you ever forget, just lay out a simple, straightforward curve that goes from -1 to 1, and you'll be able to figure out which one is max minus min and which one is max plus min. Okay? So we know this much. The maximum minus the minimum is 0.25. Man, they just don't want to. Oh, no, they did make it easy. Excuse me. It's 0.25 minus a minus 0.25. That's 0.5 divided by 2. That's 0.25. A is 0.25. Okay?
Yeah.
cosine, because we're looking at a cosine curve, that it's not phase shifted. So C is going to be 0 if we use the cosine curve. So we know even more.
Okay, yeah.
We know that it's just x. There's no C. Plus D.
Yep.
We didn't figure out D yet. D is the maximum plus the minimum divided by 2. You'll notice that's 0 also. So there's no D. Now,
Okay.
all I need is B, and I'll have the curve. Well, B is related to the period. B is equal to 2 pi over the period. And sometimes you're solving for the period, which means the period is 2 pi over B. But in this particular case, we're solving for B. Okay? Well, what is the period? And the period is always starting spot to starting spot. You can go peak to peak. You can go valley to valley. I would use these 2 points here because they've labeled that point, and we can see where that is at. So what is the period for this function?
2 pi over period. So it'd be, hold on. I'm looking at the difference between the x values, right?
Yes, exactly. Which looks to me to be 1.1.
Yeah. Okay, yeah. 1.1.
Now, that's assuming that this right here represents the peak, and I have to do that. Well, you know what? I tell you what, let's take a different tactic on this. I can't actually tell if that's the peak. Looks like it is, but maybe the peak is right to the left of it. So let's go down and compare these 2 points because they've labeled that x coordinate, and I know that's half a period. Okay. Well, that's 6/10, right?
Yeah.
So that's half the period. So the period is actually 1.2. So this was a better set of points to use. This gave us a more accurate period. I was about to have a period of 1.1. Well, if the period is 1.2, which it appears to be, then it's 2 pi over 1.2. What's that, 5/3 pi? If I divide top and bottom by 4, I get, or 0.4, I get 5/3. So now I have everything I need. Here's my equation at the top. Y equals 0.25 cosine of 5/3 pi.
All right, and that's your final answer?
No, x. In other words, that is the coefficient of x. That's what B was. When you look at the general formula, B is the coefficient of x. Sometimes B is inside the parentheses, sometimes it's out. It doesn't really affect B, whether it's inside or out. B is still 2 pi over the period. So we're going to get the period from looking at the curve, and then we're going to figure out what B needs to be. Well, the period was a number that wasn't in terms of pi, so we still got a B. That's still a number, 2 pi over 1.2. I just simplified it to 5/3 pi. So that's our coefficient, is 5/3 pi. And that's our answer. For if I were to plug that into Wolfram Alpha, you'd see something virtually identical to this.
Okay. So that is your final answer then. That is your final answer at the top?
Uh-huh.
Okay.
You have answers? Right. You have odds on these?
I do. They're just in the back of the book.
You might want to open the back of the book to that page and mark it so that, it's always a good idea to check. Some of these can be really hard and I don't want to make a mistake and give you the wrong answer. Fairly certain that this is correct, but I'd still like to see you check it if you could.
Yeah. Okay. Sure. That's the thing. Yeah, here. Let me see. So it has here, yeah, it has 0.25 cosine. It looks like the period actually was 1.1, which is weird because if we take somehow.
Yeah, no, I understand how. Here, let me just look at what we have here is a collection of data points. We don't have a cosine curve.
Right.
And that's why there's a little bit of inaccuracy. The data point they gave us was that data point, which is not the exact bottom of that cosine curve. The exact bottom probably is between those two data points. So, but we can't tell that that's the exact top either. So we don't expect to really come up with the perfect cosine curve to match this set of data points. The best we're doing is approximating it.
Okay.
Unless they gave you the information, and perhaps they did. I didn't read this problem, but perhaps they gave you the information that the period was from that point to 1.1. And if they did, then it does change our math a little bit. But that's what's going on, is that we're looking at a set of data points here and approximating it with a curve.
Okay.
Are you good on A and B?
Yeah, I'm good there. I'm looking at these next problems and trying to figure out which one's going to be next. Hold on.
Okay. I'm curious, did you send this file as a large image or actual size?
That was the largest that I could send it. It's a bad quality photo, sorry.
It is a little poor for Apples. They usually give me my best resolution photos. And that's the only reason I ask, because I'm a little curious as to, this is a little blurry. It's still readable by me and you, so it's not a problem. It was more of a curiosity about how you sent the picture.
Yeah. Yeah, I sent it best I could.
That's fine. Yeah. No, it worked just fine. So which one next?
I'm looking here. So just a quick question. Not really. Don't need to go over the whole problem. But if I type in like an equation like y equals e to the negative x over 2. Would my calculator graph that?
Yeah, for sure.
Okay. All right. That's
y equals e to the what? Negative x over 2? Yeah. That's the same as e to the minus 1/2 x.
Yep.
And the e to the x function looks like this. Well, that negative sign means that it's going to be reflected over the y-axis, like that. But then, yeah, it would be a...
it would graph it.
It would look like this one, and it would be stretched out a little bit. In other words, that 1/2 is going to act as a horizontal stretch factor.
Yeah.
You remember vertical shrinks and stretches? Well, when it's horizontal and it's a number less than 1, then it acts as a stretch factor, so it changes that curve into something like that.
Yep. Okay, I got another question. It's on that picture that I sent you.
Okay.
Number 55.
Okay. Let's do it.
Yeah.
So, radical signs don't work particularly good in calculus, as you've discovered. Well, they don't really work very good for logarithmic functions either. And when you're trying to use your properties of logs to expand the function, you got to first of all write it with fractional exponents, not radical signs. So how do I write that with a fractional exponent?
I have no idea.
Well, it's whatever's inside the parenthesis or the radical sign, and I'm going to take it to the 1/5 power. That's what the fifth root means.
Oh, right, okay.
Okay. Now,
yep.
That is the same as, and it's actually a little easier to do this if we split it up. That happens to be the same as this. With me?
Yeah.
Okay. Now, properties of logs means that if I am dividing, then I am going to subtract the log expressions. If I am multiplying, I'm going to add them. I am dividing here. Therefore, this is going to be the natural log of 4x squared minus 1 to the 5th minus the natural log of 4x squared plus 1 to the 5th, to the 1/5, excuse me. With me, as all I did was split it up. Because the argument, there's division going on, then it's the log of the numerator minus the log of the denominator.
Yeah.
Now, the next rule of logs lets me take that exponent of the argument and move it in front on the algebra line. So it becomes 1/5 of the natural log of 4x squared minus 1 minus 1/5 of the natural log of 4x squared plus 1. I've lost the exponent.
Yep.
Now, there is one other thing I can do to simplify this totally, or to expand it a little bit more. I'm trying to figure out if I should do it. I think maybe I should. If I take this first term here, it's 1/5 natural log, and I've got the difference of perfect squares in there. So that's 2x minus 1 times 2x plus 1 minus 1/5 natural log, and this I cannot factor. There is no factoring for different or sum of perfect squares. So I can't simplify the one on the right, but I did break the argument up into the product of two things. Okay, which means I can expand it further. And I'm going to do it over here. That is going to be 1/5 the natural log of 2x minus 1 plus, because multiplication is going on, 1/5 the natural log of 2x plus 1 in parentheses. And I still have this minus 1/5 natural log of 4x squared plus 1. So there's your final answer, fully expanded. Now, I've got arguments here that have things added and subtracted inside the argument. You can't do anything with that. The log of a plus b, log of a plus b is equal to the log of a plus b.
Yeah.
Definitely not equal to the log of a plus the log of b, because if I had the log of a times b, that would be equal to the natural log of a plus the natural log of b.
Yep.
So you got to be a little careful when that you don't mix up the rules. That you're only dealing with arguments where you have multiplication or division or exponentiation going on. In other words, we were taking this whole thing to the 1/5. At some point, I'm going to bring that 1/5 down in front. And I can do it at various points. I decided to do it like this because it kept everything straighter in my mind. In other words, once I took the numerator to the 1/5 and the denominator to the 1/5, then I'm able to go into that comfortably without figuring that I could have moved the 1/5 down immediately, and then I'm just going to have 1/5 times everything else, and it's still this answer. Notice that every term is still being multiplied by 1/5 in front.
Yep. Okay, fair enough. All right, now, let me see here.
So we got, we don't have a lot of time, do we? We start at 10:30, is that correct?
I think, oh, yeah. Yeah.
Yeah, and I do have an 11:30 today, so I don't have any flexibility, so we got about 2 or 3 minutes.
Okay, can I buy another hour from you? Is that possible?
Unfortunately, not today. I'm booked solid today. Yeah, I could. Oh, man, I got like 6 appointments. This guy, Merrick Weaver, usually doesn't take all of his sessions. He'll cancel one of those or only do a half hour on one of them. So maybe later on today, I could fit you in for another session, either a half hour or an hour. I do either online. You can schedule half hour or hours.
All right.
Will that work?
Oh, what time?
Well,
I'm busy late.
It looks like, what time is it there now? I know Arizona doesn't go on daylight savings time, so it's not 11:30 there, is it?
No, it's 10:30 here.
10:30, okay. So my time that's going to be available later today is going to be 4 to 5, possibly. I wouldn't want to do an hour there. And then a half hour at 6, and then at 7:30 I've got some times.
Okay, well,
I can definitely give you a half hour the rest of the day, regardless of what everybody else does. And I might be able to give you another hour. Kind of depends.
Okay. Yeah. What about the half hour at 4 o'clock? Can I do that?
Sure. You want me to just put you down for that right now? I can do that.
Yeah.
And that way it won't even depend on anybody else. I can certainly do that. What's a better phone number to text you? In other words, in the future, I won't call you to start a session. I will text it to your phone number.
Okay. Here, yeah. 704 451 4884.
Okay. I'll change that in my contacts list to make that your phone number. And this afternoon, that's all I'll do is text you the meeting ID number, that 9-digit ID number, which changes with every session. And then just open up your GoToMeeting application, put that in, and we'll be in a meeting.
Okay, awesome. Thank you.
You're welcome, Cade. Cade, nice meeting you, and I will talk to you later on today.
Yep. All right. Sounds good. See you later.
Bye-bye.